insert this into here, and this equals the integral from minus infinity to plus infinity of psi of k. All right? Now it's going to be times the limit as b goes to infinity of this stuff, 2 sine k minus k prime b all over k minus k prime dk.
And are you going to take like the derivative of the numerator of that and it's going to cancel out or something or not?
Well, I'm not going to do it. I'm just going to use the result.
Yeah.
What you have to do is you have to do this stuff called calculus of residues.
Oh, okay.
All right? So you do calculus of residues. All right? And, you know, this is going to be a little bit of magic for now. All right? And when you get all done with this stuff, you end up with equals, okay, 2 pi times psi of k.
Obviously.
Yes.
I told you that to begin with.
No, so look, it's tough stuff, all right? But what ultimately happens is, what have I isolated over here, and what have I gotten rid of? I got rid of all this stuff, e to the ik's. And what am I left with? The psi k over here, all by itself, with a 2 pi.
Didn't you have to?
And then where did that root 2 pi come from that we dropped earlier?
Well, so now let me kind of show you the result, all right? So therefore, if you use this result, so I'm invoking a little bit of magic, which I don't particularly like to do, but it's not 100% magic, all right? So what you end up with is the following, is that psi of k equals 1 over 2 pi times the integral of psi general of x, and t equals 0, I'll put it in there, times e to the minus I k, and now, you know, it doesn't matter if I call k prime or k anymore, so I'll kx, kx dx. Okay, let's go back over here. Let's write CNs. What does CNs equal to, guys? It equals minus infinity, integral of minus infinity to plus infinity of psi general of x and t equals 0, and then psi n star, right? Now I get psi dx, right? Right, where this is, oh, so this, you know, if you now that you mention the complex conjugate, it works out beautifully. Okay, because watch what happens.
Right.
Over here, so this is like you're taking the original wave function at time equals 0, and you're multiplying it times the basis set complex conjugated, and integrating over dx, right?
Since the original one was a positive ikx, it's now a negative ikx.
Very nice. Really nice, huh? You see that? So we're doing the, forget the 2 pi for a second. We're doing the exact same thing, right? Is that the same? Yeah. What is this thing? It's just the spatial part of the stationary state, complex conjugated, which gives us the minus ikx, because the original stationary part is ikx. So this is, it's the same thing.
The ikx is 1 over the square root of 2.
So that's what I want to show you. So, look, this is all the same. You guys agree? All right?
Square root.
So here's let me conclude the thing, so you'll see the difference between what I did and Griffiths did. Griffiths writes the following. Well, here's how I do it. This is me. And then I say psi general of x and t equals just the integral from minus infinity to plus infinity of psi of k e to the I kx minus omega t dk. Okay, so I put, and what Griffiths does, let me kind of do, Griffiths does the following. Griffiths puts a 1 over the square root of 2 pi here, and instead of this, Griffiths puts 1 over the square root of 2 pi there. So what happens to the 1 over the square root of 2 pi? I suck it all up into here in terms of 1 over pi, right? 1 over 2 pi. Everybody agree? So if you did Griffiths things, you take this thing and you plug it in here. You have the 1 over square root of 2 pi, 1 over the square root of 2 pi. That gives you 1 over 2 pi. I just leave it right there. So that's the only difference. Everybody agree that in the end down here, you're going to get a 1 over 2 pi. Right. Okay? So that's really nice about that whole thing. Really ties everything together. So truly, the only difference that we're doing here is we've got, from our original thing, this was our discrete summation, is that psi general of x and t equals summation over n of Cn psi n's, sine n of x and t. All right. Really, the only thing that we're doing here is that this now, our psi k dk is like our probability, right? That's our probability, as opposed to a discrete probability. And then otherwise, it's exactly the same, except for that one factor, 1 over 2 pi.
And then when we had the space representation, we lost the time dependence. So now that we have the wave representation, are we losing the space dependence?
Well, so here's the scoop, is that our solutions are still going to be stationary. But when we look at the wave packets are going to be sum of these stationary basis sets. And what happens when you add together a bunch of stationary wave functions? So look, 1D well, we had the stationary solutions, right? No time dependence. But if you add it together, if it turns out that your general function was a linear combination of stationary state solutions, then did you have time dependence?
Yeah.
Yes, you have time dependence. And Griffiths went through a problem. I had you do that problem, an example problem. So if you take stationary state solutions, don't have the time dependence in the expectation values, period. But what are general solutions? Are general solutions one stationary state, or are they a sum of stationary states? A sum of stationary states. Does the sum of stationary states have funny time dependence?
Yes.
Yes. The same thing here. The stationary state solutions, non-physical and everything, will still have no expectation values, that change as a function of time. But the real answer to what real particles are very definitely a continuous sum of the basis set. And so that will have time dependence. And that's what we're going to kind of look into next. All right? Okay, the reassuring stuff is a little bit of magic here. I don't like it, but I'm not going to do the math that goes to here. Take me a long time to redo myself. All right? You got to use the calculus of residues. You got to integrate over a pole and all this stuff. How many people have heard of calculus of residues?
I've heard of it, but don't know how.
Okay, so I only did residues in graduate school. I very definitely do them in undergraduate. All right, so it's not what I'm going to do here. It takes us too far off. All right, you do calculus of residues and you get that answer.
We just know that you took a k prime, and then you said that like this imaginary thing, so that there only happens when k prime equals k.
Yeah. So what I was trying to do is show you the flavor of the trick.
Right.
So you remember the flavor of the trick with discrete things, to find the psi n and multiply by psi n and use the delta function. And then that gets rid of it, isolating the CNs. The whole reason I went into this part
just to show the flavor of that.
Is to show you the flavor of the Fourier trick extended to the integral.
Because k equals k prime only goes to 0 anyway.
Right, so there's something going on at 0, and that's when you do this residues. And whenever you do the calculus of residues, you got to integrate and integrate over a little circle, and let that little circle approach 0. So if you have a singularity at some point, what you do is is you come out and you integrate around that circle,
Yeah.
around that point, the singularity,
Huh.
and then you make the size of the circle be epsilon, and then you let the epsilon shrink to 0 in the end, and you get a finite number. It's very nice stuff. Okay, not what we're going to do. In the end, how much different are we doing from the discrete case to the continuous case?
Not much, a little bit different.
Yeah, not too much. Okay, let's do an example. So,
So if we're solving though for the free particle,
we're doing free particles, yeah?
right, and we're not employing any of this, because we're going to do something else,
I don't know what that means.
well, we're not going to use that, because you said that was just something you wanted to show us the flavor of.
I showed you the flavor of Fourier's trick
Right,
for the integral
okay,
to get this result.
all right.
So the big scoop is we use Fourier's trick for discrete space, which you guys have to be able to do,
Yeah.
all right, to get this result. What I did is I showed you the flavor of that trick extended to continuous variables. Well, we did have to stop at some point, but you got the idea of what it's doing, right?
Right.
And then we got the result. And so now we're just working with the result.
So that's the result of the new.
That's the result.
Yeah. It's like the same thing, except that the C ends in a non-continuous sum, and then this is the phi ends, the phi k's.
That's what I love to hear. When I hear people say it's the same thing, oh, it's just this. That means you're pulling it all together, all right? It's very nice.
Trying.
Didn't you say you
Yeah.
wanted to solve for?
I tried to solve for psi k, and I just did.
Okay.
Yeah, psychic. Okay, let's do a problem. Here's an example problem.
That's phi.
5. Oh, that could be reading. Dino, you're supposed to help me. That's 5.
I didn't want to be like the guy that always brings it up, you know?
I need it, Dino. I'll pay you, all right?
Just, yeah.
I guess next time I'll bring it up.
Yeah, please do. I really need it, okay? Let's do an example. This is example problem 2.6 in your book. All right? Oh, here's Dale. He's looking up calculus of residues. We'll have it for us all by the end of class, all right? He's intrigued. He can't put this down now. It's going to drive me crazy for days.
That's how science gets done.
That's how you should do it.
I'm
Yeah,
completely fine with that.
yeah, good. All right. So look up on the web if you want to count. It's really nice to do. It's about when you have these integrals where you're integrating over some place where there's a like a 0, a singularity, and so you got to have a way of doing that integral. Okay, so let's do example problem 2.6 in your book. So this is a nice. You think it's going to be a mess, but it's going to be nice and easy. I need pens already, but you believe it. So let's do it in green, like those two are dead. All right, we still have a way to go for today. All right, so again, Harris is great for this whole section. Harris, the modern physics book, this whole section of Griffiths. Griffiths goes by very quickly. All right, you'll want to read chapters 4 and chapter 6 of Harris. Pictures, diagrams, details, very nice stuff. Okay, so here we
Would
go.
that be helpful for the test on Thursday?
Sure. I think so. What your test on Thursday should be everything I do in class, at the level I do in class, and the idea I do in class. Right? So if that helps you do with the things I've done in class. When you guys love it, if I say, okay, do calculus of residues and do that.
Yeah.
I would not do
I wouldn't love it.
that. I would not. I throw my Okay, there you go. I would deserve it. Okay, so example, free particle.
Never mind.